it going, Matt?
Hey, pretty good. How you doing?
All right.
Can you hear me?
All right. I guess we'll go ahead and get started. Last time we spoke, well, for starters, do you have any questions?
No,
Any,
no question.
your audio's off. Sorry about that. Did you have any questions on any past material or questions about the course or anything, Matt?
Can you hear me now?
Actually, your audio is fine. I'm the crackhead. I completely forgot about my headphones.
Yeah, nah, no questions for me. No.
I just like how confidently I said your audio is off.
I was trying to figure it out.
Sorry about that. So, did you say you had any questions, or are you good?
No, no questions.
Cool deal. Have you taken your test yet?
No, I scheduled it for Tuesday.
No problem. Yeah, plenty of time. Good deal. All right, we'll go ahead and get started. When we last spoke, I had talked to you about Ohm's law. I told you about how we make batteries or how you can make batteries. I didn't tell you too much about the modern technology that, for instance, Elon Musk and various other people and companies are making, but I did explain to you, a way to make batteries. And we talked about resistance and current, the units that they have. We did kilowatt hours and we did amp hours, two different units that come in handy from time to time. So right now, I just wanted to show you an example with regards to Ohm's law that's pretty straightforward. So I'm going to go ahead and share my screen with you. And by the way, the videos are posted. I know I tell you this just about every time, but they're posted to my YouTube channel, and usually I do it the same night of, but sometimes it takes me till the next day. Last time I definitely posted it the night of, and I'll probably do the same tonight. Unless I have to do a lot of editing, I can usually do it on the same day. So in this first example, and you'll see these examples are very much like the ones used in the book. I try to change them enough that it won't, quote unquote, be a copyright violation. I'm trying my best not to violate copyright, but also at the same time, Giancoli has a really good feel from his years of experience of not only teaching, but also writing books of, the sort of the minimal examples you need in order to make sense of the chapter and be able to survive the homework. So that's why I try to mimic some of the examples that he gives, as well as sometimes I make up others. This first example says a flashlight uses 375 milliamps while its batteries have a voltage of 1.58 volts. A, what is the resistance of the bulb? And B, assuming the bulb's resistance is a constant, i.e., the bulb is ohmic. That's if you're reading, you probably already learned that when we refer to something that has a fixed resistance, we call it ohmic. So that's why I wanted to point that out in that question. It says, assuming the bulb's resistance is constant, what would the current be if the battery voltage dropped to 1.20 volts? So last time I did tell you, for instance, that basically AA, AAA, C, and D batteries all have a quote unquote nominal voltage of 1.5 volts. But generally, when you actually purchase them, they'll typically have voltages from 1.67 to 1.72. I think I maybe even seen 1.75 volts before. But as time goes by, that voltage that you measure, especially if you measure it while it's current's being drawn out, that voltage that you measure will drop, and that's slowly how they quote unquote die. Once that measured voltage drops below 1.5, they're no longer quote unquote fit to be used per manufacturer's specifications. Because what happens is, even if especially if you're checking them without being connected in a circuit, if you connect them to a voltmeter to measure the voltage and it reads less than 1.5 when no current is being drawn, then they're going to drop even more when current's being drawn, and you sort of go on the assumption that all batteries, when you design something that takes, double A, triple A, C or D batteries, you design them to be worked with 1.5 volts. So let's go ahead and start with that. Our solution is going to require Ohm's law, which says V equals IR. I will tell you that when we start working with electronics and electric circuits and stuff of that sort, that's an area where we tend to keep the prefixes. So we often will keep the amps and milliamps or even microamps, and we'll keep the volts and volts, but sometimes kilovolts as well. So just be advised and pay attention to how I do that on occasion, because I'm doing it usually to show you how we normally use it. So let's turn to part A. Part A says, what is resistance of the bulb? What we say is obviously the voltage across the bulb, V, is equal to the current through the bulb. Notice the wording I'm saying here. This is a big important part. Your author does this as well, telling you that we talk about current through an object and voltage across or on an object. So the voltage across the battery, meaning if you took or excuse me, across the bulb, meaning if you took the positive terminal of your voltmeter and attached it, say, to the threads of your light bulb, and then you took the black terminal of your voltmeter and touched it to the nub on the bottom of the bulb, that would be the voltage across the light bulb when it's actually connected. Uh, that voltage is equal to the current that goes through the bulb times the resistance of the bulb. So we're in the process of wanting to find the resistance of the bulb. And normally I like to solve the equation for the variable we're solving for and then plug the numbers in. This time I'm going to leave them, I'm going to put the numbers in like a normal student often works, so you can see a little bit about how I can keep the prefixes. So what I know is the voltage is 1.58 volts and the current is 375 milliamps, and that's equal to 375 times R is equal to 1.58 volts, and therefore we get R is equal to 1.58 volts divided by 375 milliamps. Now, a milli is 10 to the negative third, and a 10 to the negative third in the denominator is the same as a 10 to the positive third in the numerator. So this would actually make a 10 to the positive third amount of ohms. So if I just did 1.58 divided by 375, that would come out automatically in kilo ohms. So I'll show you that now, plugging in the numbers once I turn my calculator on. 1.58 divided by 375 is equal to 0.00421 Notice I'm putting them in pods of 3 again. 3. And as I told you, since we were dividing by milliamps, that was 10 to the negative third in the denominator, which becomes 10 to the positive third in the numerator. And 10 to the positive third is the same thing as the coefficient, or excuse me, as the prefix kilo. So that's in kilovolts, and this gives me two extra digits. We had three sig figs on everything, and I've written two extra digits. Now, if I want to convert that back to volts, I just basically multiply by 1,000, and that will give me 4.213 space 3 ohms. So that is the resistance of the bulb. Again, we're going on the assumption that this resistance is fixed, but in reality, it very much will not be fixed. In fact, if you measured the voltage of the, or excuse me, if you measured the resistance of the bulb when you had a very small voltage across it, say zero point 0.1 or zero point 0.2 volts, you'd get a very small resistance. And if you did slightly higher voltage, you'd get a slightly higher resistance. And if you did higher still, you get a higher voltage. And in fact, what you find out is the voltage is highly dependent on the temperature with the light bulb. Therefore, the higher the current going through it, the higher the temperature, and therefore the higher the resistance of the light bulb. Now, that being said, we're going to pretend like that reality doesn't matter to us. And this is just sort of a first order approximation. So if you inadvertently put 1.20 volts across the light bulb instead of the nominal 1.5 volts or the 1.58 volts that we had, then you're going to get a different amount of current. So what we want to do now is find out what would be the current through the light bulb when the voltage is now 1.20 volts. So, oops, part B, we work as follows. Again, we have V is equal to IR, which is Ohm's law. This time the voltage is going to be 1.20 volts, and that's equal to I times 4.21. Now, this is where me keeping two extra digits comes in handy. So I have these two extra non-significant digits, and therefore when I do the math, I get a more complete result. This will give me that the current is equal to 1.20 divided by 4.2133. Oops, something bad just happened. I just erased everything somehow. 1.20 divided by 4.2133 gives me 0.284. And keeping it in pods of 3, I now have an 8, 1 after that. That means the 8 and the 1 are non-significant figures, and therefore the current at 1.20 volts, I can convert this to milliamps by dividing by by multiplying by 1,000. So again, last time we went from kilo to voltage. That's going down, so I multiplied by 1,000, and now I'm going from amps to milliamps. That's also going down by 1,000, so that's why I multiply by 1,000. And in this case, we get 284.81 milliamps. And that's the current in the second scenario. Any questions on that? Now, your book does have a
No, no question.
nice and I think instructive conceptual example, and I went ahead and more or less copied the idea verbatim, specifically so you better understand why we say things like current through and voltage across or voltage on or something like that. In this case, I've drawn a little piece of wire connected to a resistor, connected to another little piece of wire, and I've named a location on the wire to the left of the resistor A and to the right of the resistor B, and we see that current is flowing from left to right. We're expecting you to know, again, that we are thinking about conventional current, which means the direction that positive charges flow. And therefore, we're asking you, is the voltage higher at A, at B, or is it equal at both locations? Okay. Now, normally I would ask the student to try to answer this, but I really don't. Even though I'm certain you'd answer it right in this case, I'm trying to refrain when I only have one or two students there because it's kind of brutal. If you actually make a mistake, you get embarrassed, which it shouldn't be, but still, just to be safe. So what I'm saying here is we know current, conventional current, which is made up of positive current or charge carriers. So you're pretending like little positive charges are moving from one location to another. And they, of course, move, as we learned in chapter 23. Yeah, as we learned in chapter 23, positive charges move from high voltage to low voltage. So that tells us since the current is going from the direction of A towards the direction of B, that the voltage at A should be higher. So I'm going to say higher V at A, and that's the first answer. And then it says, is the current going through the wire higher at A, at B, or is it equal at both locations? So when I want you or when I ask you something like current, I want you to think literally like the wire is a little pipe with charges going through it, and every time you come to a junction where that wire breaks off into two or more wires, you want to think as if it's a manifold where one pipe comes in one side, reaches a Y or an elbow or something, so that it can break into two subsequent pipes. And then you want to think about all the charges coming in through one pipe and then leaving through two. Then, if you remember that we told you charges cannot be created nor destroyed, that's the law of conservation of charge, then you usually can reach the right conclusion about such questions. So in this case, we have a single pipe that's coming from the left of A through A and in through the resistor, which you can also think of a pipe, but you might think of it as a pipe with like tree sap on the walls or something, something that would compel it to slow down or not move as efficiently or something like that. Then followed by yet another pipe to B, and then followed through B past B. So if you think of that, you really only have one pipe. So every bit of charge that goes through E must go through B as well. And again, that's just straight from conservation of charge. So it is equal current at A and at B. So there's your two answers. Make sure you ask me questions if you have any. I'm
Sounds
sure.
good. No questions.
Thank you, sir. Appreciate that. Uh, so now let's look at example two. Your book does an example with speaker wires, and I think that's a good application because a lot of college age students often have to run speaker wires, or like me this weekend, I just ran uh, some cables for. I'm sorry. Sorry about that. Some cables in my vehicle for actual cameras. So I actually got something from Temu for like 156 bucks, where I've been seeing them selling for upwards of 800 and even $1,200 for the kit. But now I've got 60 meters of cable because it's made for a Mack truck and I just have a F350. But the common thing is, yeah, you have to run wires from one part of the car and specifically often from the battery to like the radio, and then from the radio to a speaker and then back and stuff like that. So in this scenario, we're wishing to run about 20 meters of copper wire and keep the total resistance below 0.090 ohms. Now, what you know is from Ohm's law, V equals I times R. So what that means is when the current going through the wire goes through the wire, the voltage is going to have to drop if the wire has any resistance whatsoever. And of course, wire always has some resistance. It's just usually way smaller than than the resistance of the other things in the circuit. And that's quite often the case with speaker wires as well. So, for instance, if you took all this time to get you a speaker that put out a high voltage, for instance, maybe you made one that could make really loud sounds and ran on a voltage that's higher than 12 volts or something like that, then it would be self-defeating if your wire was so resistant that it cut the voltage down from, let's say, 16 volts back down to 12. So that's why you would want to limit the amount of resistance a particular wire might have. So that's what we're doing in part A, is figuring out if we want the resistance below 0.090 ohms, what criteria should the diameter of the wire meet? And then in part B, it says if the wire is to carry 5 amps, by how much will the voltage drop from one end, namely the end at the power supply, to the other? Okay, so that's our question. I'm going to say solution And now I'm going to state another equation we covered, and that equation was R, the resistance, is equal to rho, the resistivity, times L, the length of the wire, divided by A. Now, I will tell you that the resistivity of copper, I'm looking this up in table 25.1 from your textbook, and the resistivity of copper is 1.68 times 10 to the negative eighth ohm meters. So all we have to do is figure out what is the diameter. Now, we know the length is L, we know the resistivity is rho, we know the R needs to be less than or equal to 0.090 ohms, and we also know that a wire generally has a circular cross section, so the area should be pi r squared. I should use a different r because that r is the same r I used for resistance. So I'll say pi r squared. But we know the radius is the diameter divided by 2. And since we're wanting to solve for the diameter, it might be smarter for us to substitute d over 2 for r, in which case we'd solve directly for d instead of r. So doing that, I replace the r with d over 2. Of course, it's squared, so this ultimately makes pi d squared over 4 as the area for the formula for the area. Now that we have all that, we can say r equals rho L over pi d squared with 4 on top. Therefore, we can say 0.090 ohms is greater than, oops, is greater than or equal to, I'm going to put in 4 for the 4 that was in the numerator, times the rho, 1.68, times 10 to the negative 8 ohm meters, times the length, which is 20.0 meters, divided by 3.14159, that's close enough for pi, times d squared, and d squared is what we're solving for. So again, I'm trying to put this in uh, where I put the numbers in before solving the formula for the specific symbol, so it's more like what students tend to do. So manipulating this, I can ultimately get that d squared has got to be greater than or equal to. Now I'm going to compute all these numbers, and of course the 0.090 is going to be in the denominator multiplied by 3.14159. So I'm going to go ahead and compute the numerator and denominator so you can see what I got there. That's 4 times 1.68 times 10 to the negative 8 times 20.0. That gives me 0. Well, I should have written this in scientific notation, but oh well. There's 3 zeros, and then it's followed by 2 more zeros, and then a 1, 3, and a 4, 4, trying to keep these in pods of 3. Using only 3 sig figs, obviously this 4 and this 0 are not significant figures, and this gives me ohms times meters cubed, or excuse me, ohms times meters squared. And then the denominator is going to be 0.09 times 3.14159. And that gives me 0.2827431. So I'm going to take the 0.000001344 divided by that previous answer using my answer key. And remember that previous answer would technically have units of of ohms. So now I just get meters squared for the answer. So it's going to be 0.0000004 and then 753 and then 4. And this gives me meters squared. And obviously, I only have three sig figs, so this 3 and this 4 are not sig figs. And this means that D should be greater than or equal to the square root of that. So I'm going to raise that number to the zero point 0.5 power. And that's going to give me 0.0021802 meters, which is equal to 2.1802 millimeters. Again, the last two digits being not significant. So 2.18 millimeters are larger, and that's what I meant by the criteria the diameter should meet. This says the diameter needs to be at least 2.18 millimeters or larger. Okay, so there might have been some ambiguity if you didn't necessarily understand how resistance and diameter and area and length were related. There might be some confusion as to whether it would be better to have a smaller or a larger diameter. And in this case, you can see to get a smaller resistance, you actually need a larger diameter. So that's why we are allowed 2.18 millimeter diameter or larger. So I'm going to say this is equal to the diameter, and I'm going to box it off like that. Now for part B, it says if the wire is to carry 5.00 amps, by how much will the voltage drop from one end to the other? So I'm going to go on the assumption that the resistance is actually going to be 0.090. I know I said below it, or I should have said below it or equal to it. But anyways, that's what we're going to treat it with. I'll write the I'll write A next to that part. Now I'm going to write B here. So what we want to do is we want to say V is equal to I times R. And in this case, we want to actually know V. So we're going to put in the current, which is supposed to be 5.00 amps. And then we're going to multiply that by a resistance of 0.090 amps, or excuse me, ohms. And the important thing here is remember, I did say that we wanted the resistance to be below that. So what we can tell is if we actually put the resistance at that, the current is going to be a little bit smaller than it should be. Or excuse me, the voltage is going to be a little bit larger than it should be. So we would actually get a slightly smaller voltage change in this, but 5 times 0.09 obviously would be 0.45 amps. So 0.450 amps, which is 450.00 milliamps. Or what was I saying? I'm sorry about that. 0.450 volts is what I should have said. I don't know why. This is twice in this one problem I tried to write a wrong unit for something. But anyways, it obviously should come out to be volts. And since this is 0.450, we could leave it as volts, but we could also say 450.00 millivolts is the voltage drop. Now you can see that this is a little better than like I was advertising. Like I said, maybe you bought a system that allowed you to bump up the voltage of your stereo system from 12 volts to say 16 volts, and then that would allow you to make louder speakers and stuff of that sort. If that was the case, and you had to deliver 5 amps to your speakers from that power supply, then it would come out at 16 volts and then go through the wire and not drop, but down to maybe 16.5, or excuse me, 15.5 volts. So that's the advantage of having a smaller resistance wire is you get a less of a loss of voltage from one end of the wire to the other. That's something important to keep an eye on as we talk about, for instance, power lines and stuff of that sort going over big country fields. You've probably seen those really, they call them high tension lines, and those would be the ones that are on those really tall towers you see go through the mountains or farmlands or fields or prairies and stuff like that. And basically, they carry those at extremely high voltages. Like it's not uncommon to find out that the voltage of those wires might be 500,000 or even 1 or 2 million volts. And what we've discovered is that when you actually use this type of AC current, that if you use a step up transformer to step the voltage up from, let's say, house voltage, which would be what we call 120 or 125, if we wanted to step that up to 1.25 million, then we could run that through a step up transformer that has 1 million more turns on the opposite side than the incoming side. So if you had, say, 10 turns on one side, you want 10 million on the other side, and in would come 1.25 volt, or excuse me, 125 volts, and out would come 1.25 million volts. I think I might be off by a factor of 100 there with that quick thinking I did, but you get the main point is basically whatever factor you want to increase the voltage by, you have to have that many more turns on the output side of the transformer than you had on the input side of the transformer, which we'll discuss later. Okay. But the good news is when you do that, when you increase, let's say, the voltage by a factor of 1 million, it turns out you decrease the current going through it by the same factor. And that's just because conservation of energy says the power in at best is equal to the power out. It certainly can't put more power out than it came in. It's almost always going to, or it's always going to put a little less power out than it does in. So power turns out to be current times voltage. So if the voltage goes up by a factor of 1 million, the current must go down by a factor of 1 million. And it's that current going down by a factor of 1 million that makes that power going at millions of volts much more efficient, because it turns out the equation for power, which I've hinted at before, and I just did it again. Power is P equals IV. But if you use Ohm's law to get rid of the V, for instance, you can say P equals I. Now I'm going to replace V with IR, and you get I squared R. That's the reason that you step up a transformer, because basically when you run power from a power let's say from a power plant, whether it be hydroelectric or solar or whatever, when you're delivering that power from the power plant, basically it serves, let's say, X number of homes. Like you build a power plant and you say, okay, this is going to service these 3 neighborhoods, and these 3 neighborhoods combined give us 100,000 homes. Well, 100,000 homes, and let's say just 100,000 homes, no businesses. Businesses have different amounts of current and stuff they need. But in general, the standard supply of electricity from a power company for a home is what we call a 200 amp service. So if you have 100,000 homes, then that you're covering, then you have to multiply that by 200 amps per home. So you get 200 times 100,000, that gives you 20 million amps. So 20 million amps squared multiplied by the resistance of the wire, which may be very many miles away, that can lead to a lot of power that's lost as heat. So if you instead step up the voltage by a factor of, like I said, 1 million, then you're going to step the current down by a factor of 1 million. So instead of 20 million amps, you're now only supplying 20 amps. So now you've got 20 squared times that same resistance. That's why they run those power lines at such high voltage, because it saves them a ton of electricity. Now, I'm getting ready to make a third version of this power equation, and the third version of this power equation is going to look like it contradicts the second version. So be careful here, but and I'll explain it in a second. Let's say we take the original result, the P equals IV. So just looking at this part right here, looking at this, and then using Ohm's law, which is V equals IR, we can see that V equals IR gives us that I is equal to V over R. So I can plug V over R into I, and when I do that, I get V squared over R. And this is why I'm saying it looks like it's contradictory, because I just finished telling you if I step the voltage up from 125 volts to 1.25 million volts, then I get less loss of power due to heat. Now, the important thing to understand here is when I was talking about the speakers, I mentioned to you that if we imagine someone had bought a speaker system that allowed the radio to work at 16 volts instead of 12, car batteries normally 12 volts, that's why I said 12. But if we went up to 16, that'd be 25% higher voltage and potentially 25% higher power, and therefore, a louder, more robust stereo. So, in doing that, I said it's important that we not take that 16 volts that we just stepped up to and use it all in wasting the voltage in going through our wires from the stereo to the speakers. So the reason why I'm pointing that out is there was two voltages we were talking about. There was the voltage of 16 volts that the power supply is now acting as if we had bought that new quote unquote speaker and sound system. And then there's the voltage drop across the wire. The voltage drop across the wire is the V that we're talking about in P equals V squared over R. It's not the fact that we went from 12 volts to 16 volts. It's not the 16 volts that matters. It's the voltage drop across the wire. The same thing is true with electricity. It doesn't matter whether the voltage is at delivered at 125 volts, or if the voltage is at 1.25 million volts. What matters in V squared over R is what does the voltage change from one end of the wire to the other. So, if you send the voltage out at 1.25 million volts, and when it got to the other end of the wire, it was now only 125 volts, then yeah, V squared over R would contradict I squared times R. But that's not what's happening. What we're doing is we're using the wire to calculate the voltage, and that wire would be calculated by taking the 20 amps. Remember, I said it was 100,000 homes times 200 amps per home. And then I said that would equate to 20 million amps. So that 20 million amps is what's going through the wire, and that's why you multiply that 20 million by 20 million again times R, the resistance of the wire, to get the power dissipated. If you wanted to use the V squared over R formula, what you'd have to do is figure out what is V equals IR for the wire. So you say, okay, I'm going to take the voltage of the wire, or I'm going to take the current that goes through the wire, I, which is now, since we used the step up transformer, which stepped the voltage up by a factor of 1 million, Now the current, which was 20 million, is going to step down by a million. So now the current's only 20 amps. So you'd multiply that 20 amps times the resistance of the wire, and you'd find out that that is much, 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 much smaller than the 2 million volts that we're talking about. In fact, if we were talking about 20 amps, a typical resistance for a wire, even miles of wire, might be 5 ohms with the kind of wire that we use here. So if I multiply 5 ohms times 20 amps, everybody knows that's going to give you 100 volts. So really the V squared that we would be talking about there is on the order of 100 volts. Meaning we put out 1.25 million volts, and when it got to the other side, it was now 100 or 1,249,900 and or 900 volts because we're 100 volts shy. Okay, hopefully that makes some sense. And this also, like I said, is another set of equations that will come in handy. We'll Your book derives it for you. I just want you to know those three results, and that comes up in this chapter anyway. So I wanted to go ahead and cover it. Another thing I wanted to mention while we're here is we mentioned rho equals resistivity, and the units of rho is ohms times meters. Well, there's also a quantity called sigma, not to be confused with the 15 other sigmas we've used in the class to date, but this one's called the conductivity. And the conductivity is defined to be 1 over rho. And here's probably the main reason I want to cover it because I really just like this. The dimensions for the conductivity are 1 over omega meters. Oops, I didn't write that clearly. If you heard me, then you know exactly what the units were, but if you were just looking at it, it wasn't obvious that I wrote ohms times meters. Uh, but here's the part that I'm excited about. The 1 over ohm times meters, so the ohm meters to the -1 power is called a mho. And that just makes me laugh and smile a little bit because us physicists have done a lot of things that are kind of really nerdy and not are lacking excitement. Like the first particle we discovered, we named alpha. The second one we named beta, and the third one we really went off the farm and said, let's call it gamma, right? So at least in this case, we took a little bit of imagination and did something different. But anyways, that's what conductivity is, and that's what it's measured in. And really, it's just whether you want to talk about conductivity, where high conductivity means it's a good conductor, or do you want to talk about resistance, where a high resistivity means a high resistance. Okay. All right, now that we've done that, we can go on to some other stuff. And one of the things I want to show you is this concept. Let's imagine having a two pieces of wire. Let's imagine having one piece of wire. Let's say this blue one right here is copper wire. Now, it could be aluminum, it could be gold, it could be silver, it could be all sorts of stuff. It could be even iron. The main thing is it's a fixed amount of fixed material, period. Okay. Now, what we're wanting to do is think, what if I were to grab the ends of that short, fat piece of wire and pull it really, 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 really hard and stretch it out so that its length is now 3 times L instead of just L. If that's the case, I would like to know what is the new radius R equals question mark and what is the new resistance. and I'll call that R2 equals question mark. So, solution. The equations we're using here are R is equal to rho L over A, and conservation of mass turns out to be a thing. Now, I will tell you, in light of relativity, conservation of mass and conservation of energy are no longer valid. There is no such thing as quote unquote conservation of mass. There is no such thing as conservation of energy. There is now something called conservation of mass energy. And it still looks just like conservation of mass is obeyed, and it still looks like conservation of energy is obeyed, as long as you're not dealing with things that are quote unquote relativistic, things that are moving basically at 1% of the speed of light are faster is a good way of estimating it. And in terms of gravity, if the gravity is not terribly intense, then general relativity need not be applied either, except in some odd cases. But the main thing is we're not dealing with relativity, so we will pretend conservation of mass is a thing. And we know that, sorry for this row is density is equal to mass over volume. So what that means is when we're going to calculate mass, we have to say that mass is density times volume. And that means the density in the second part is equal to, or times the volume of the second part is equal to the density in the first part times the volume of the first part. So that's the way we do this. Now, again, we'll also go on the assumption that copper's density is not going to change. So really, we're just you can sort of think of it as conservation of number of molecules, or in this case, conservation of the number of atoms. Either way, its volume initially equals volume finally. So volume one for this particular thing, the object on the left, is of course pi r1 squared times L. The volume for the second thing is pi times R2 squared times L2. Now, L2 is actually equal to 3L, so we can say pi R2 squared times 3L. Now, conservation of mass. Conservation of mass gives us pi R1 squared L is equal to pi R2 squared times 3L. We can immediately see that the pi cancels out and that the L cancels out. So now we have R1 squared is equal to 3R2 squared. So if I wish to solve for R2, all I have to do is say R2 is equal to R1, I'll say R2 squared is equal to R1 squared over 3. And finally, I get, by taking the square roots of both sides, I get R2 is equal to R1 over the square root of 3. Okay, and the square root of 3 is about 1.73. 1.732 if you really need. But that's the main thing we needed that. So now I have R2 is approximately R1 divided by 1.732. And I'll double check my square root of 3 just in case I made a boo-boo, but I'm pretty sure the square root of 3.5 is 1.7, yeah, I wasn't sure about the two. I was pretty confident, but just in case. So that is 1.732. Now, if I raise that to the negative one power, I get 0.577. So this is equal to 0.57735 times R1. So that's part of our answer. That's the new radius when I stretch the wire to be three times the length. Now it has a radius given by 0.57735 times the original radius. Okay, so it's about 57% the size of the original one. So what we see is the length increased by a factor of three, but the radius decreased by a factor of a little less than a half. So that's not too terrible. Now we need to do the second part, which is to compute the resistance. So R1 is equal to rho for copper times L over pi R1 squared. R2 is rho copper times 3L over R2 squared, which equals rho copper times 3L over. Now remember, R2 squared was in fact R1 squared over 3. So I'm going to write this as R1 squared over 3. And we see that it's going to be 9 times L over R1. Oops, left off the row. It's going to be 9 times rho copper times L over R1 squared. Now I can say R2, meaning the resistance of wire 2 divided by the resistance of wire 1 is rho copper L over pi R1 squared. And, oops, both of them left off a pi. There was a pi in here, everybody. I don't know why I left it off. It was in the first part, but I didn't put it in the second part. Anyways, now I have it. So now I'm going to say 9 rho copper L over pi R1 squared. You can see now that this whole thing cancels out with this whole thing, and that, oops, I'll make it an X so it looks right. And this rho copper cancels out with this rho copper, and we're left with, oops, we are left with 1 over 9. And of course, that means R2 is equal to 1 over 9. Should be equal to 9. Oh, no wonder I put it in the wrong spot. Ah, stupid me. Watch out, everybody. Sorry, Matt. You see what I did here? I wrote R2 over R1, but then I filled in R1 and R2 down here, so I did it backwards. Let me correct
Yeah, I
that
didn't
real.
catch that.
Yeah, I should have caught it. Wasn't paying attention. That's what happens when you change your mind in the middle of a problem and don't say it out loud. Sorry about that. So in this case, it's going to be R2. So I got to say 9. Whoa. Or I'm just randomly erase a bunch of stuff. Uh, I'm going to say 9 times the resistivity of copper times L over pi R1 squared divided by R1, which is rho copper times L over pi R1 squared. Now you can see that the L over pi R1 squared cancels out with L over pi R1 squared, and you can see that the resistivity of copper cancels out with the resistivity of copper. And finally, we can say that R2 is going to be equal to 9 times R1. So yes, you can actually stretch the wire to make it longer, but it's actually worse than just making the wire three times as resistant because, if you just took the identical wire, let's say you had number 10 wire and one piece was 10 meters and the other piece is 30 meters, the resistance of the 30-meter wire is only going to be three times as much as the resistance of the 10-meter wire. But in this case, it's sort of like we took a number 10 wire and stretched even though it was 10 meters long, we stretched the number 10 meter wire from 10 meters to 3 meters. That made it act more like, instead of a number 10, it probably looked more like a number 12 or something like that. And now it was 30 meters long, so the resistance increased not by a factor of three, but by a factor of nine. Any questions on that one?
Nope.
Okay. All right. Well, we have another concept that we need to uh, introduce you to, and this is just like what we did, or excuse me, I shouldn't say what we did. Well, yeah, that's what we did when we talked about the way that metal or material changes length when you allow it to change temperature. So, for instance, if you lay uh, iron railings for a railroad in cold weather, and then it gets hot later, the railroad irons are going to expand and cause them to buckle, and exactly why you sometimes see a little bit of railroad track go like this and then it does that. That's a result of them having welded the ends of the tracks together like they're supposed to at a relatively high temperature, but yet it still got hotter than the high temperature that they were at. So it still expanded too much and caused the whole rail to buckle. So, what is the relationship there? Well, what you can imagine, it's almost the same derivation. Basically, you can imagine that the resistivity is directly proportional to the change in temperature. So we can say resistivity is proportional to the change in temperature. I'll say delta T. Okay. Now, if that's the case, then if you go from 100 Kelvin to 200 Kelvin, and it really depends, by the way, whether you're using Kelvin or Celsius here, as in terms of talking about doubling stuff. This is equations made basically for Celsius. So in going from 100 Celsius to 200 Celsius, that's a doubling, and going from 0 Celsius, well, let's say 50 Celsius to 100 Celsius, that's also a doubling. So what we're saying is if we double the change in temperature, we're going to double the resistivity change. Another thing we need to think of is the change in resistivity is obviously proportional to the original resistivity, because if it wasn't, you'd have weird occurrences where, like, all of a sudden the resistivity was 5, you increase the temperature, and instead of it just, because you doubled the temperature, instead of it just doubling, it actually went up by a random amount. Uh, if you allow that to be directly related to the initial temperature, then it makes a little bit more sense. And you would subscript the resistivity with a T. And that just means the resistivity at temperature T is directly proportional to the resistivity at uh, row zero. Okay. Well, if you play with that a little bit, you can actually reach the conclusion that rho t is actually going to be equal to rho zero times 1 plus. You'll notice this equation looks exactly like the equation we did for thermal expansion. And actually, this one, I didn't mean to do that. The one that I wrote initially, I was going to go through a argument to make this equation to the right, and I abandoned that at the last minute. So I'm going to erase this and just say that is the relationship between the resistivity at a temperature T and the resistivity at a temperature T0, which we shall call rho zero. Okay. Now, the alpha is the temperature coefficient of resistivity. This is the temperature coefficient of resistivity. Now, in terms of a derivation, I will show you this because you can take rho t and multiply it by L and divide it by A. And then, of course, whatever you do to one side of the equation, you've got to do to the other. So now you're going to get rho 0 times L over A times 1 plus alpha T minus T0 like this. And now you see, in addition to the first equation, we now have another equation that says R at temperature T is equal to R at temperature 0 times 1 plus alpha T minus T0. So the equations are identical. You just replace the rho with the R and you'll still get the right one. There, your book does give a table of temperature coefficients of resistivity, and in fact, it's in the same table, table 25.1, as the table with the resistivities. So I'll say C table 25-1 for rows and for alphas. Okay, so let's try a problem using this new equation. There's a problem your book is doing, and I like this one. It says the variation in electrical resistance with temperature can be used to make precise measurements of temperature. Platinum is commonly used since it is relatively free from corrosive effects and has a high melting point. Suppose at 20 degrees Celsius, the resistance of a platinum resistance thermometer is 164.2 ohms. When placed in a particular solution, the resistance is 187.4 ohms. What is the temperature of the solution? So that's the problem we're going to solve here, and it actually takes a little bit more space than I have left on the page here. So I'm going to write this as example 3, and I'm going to put it on the next page. Example 3. Okay. Uh, Using a platinum wire to measure temperature at 20 degrees Celsius. R equals 164. Here's where I'm going to, yeah, here's where I'm going to try to change a little bit. Well, now I'll just do it. 164.2 ohms. And at an unknown temperature, T, the resistance is RT equals 187.4. What is T? Solution. So what I'm going to do is I'm going to use the fact that R at T is equal to R at T0, which we call just plain R0, times 1 plus alpha T minus T0, like that. And what we also need in this case is the actual alpha for platinum. So I'm looking up the alpha for platinum, and the alpha for platinum is 0.003 927. And of course, the units here, hopefully you've already managed to figure it out, but they're reciprocal Celsius degrees. So that'd be Celsius degrees to the -1 power. So what we can do is we can say RT over R0 is equal to 1 plus alpha T minus T0. So we're a little closer to actually solving for T at this point. So I'm going to go ahead and plug in the numbers. The numbers are the temperature at T is 187.4 ohms, and the temperature at T0 is 164.2 ohms. And that's supposed to be equal to 1 plus 0.003927 reciprocal Celsius degrees times T minus 20.0 degrees Celsius. So we've just about got everything. I'm going to take 187, turn on my calculator first. 187.4 divided by 164.2 gives me 1.1429. Now notice I'm using way more than the 3 sig figs that I normally use, but they gave me 4 sig figs, so I want to use 2 more than that. So in addition to the 29, I'm going to put an extra digit of a 1 after that. And when I divide two significant digit numbers by one another, I get 4 sig figs out. That means the 9 and the 1 are not sig figs. But the main thing is I know that they're not, and that's equal to 1 plus 0.003927 T minus, now I'm just distributing the point 0.003972, or excuse me, 3927 times 20, and that gives me minus 0.07854, and that is nothing but zeros afterwards. I really only had 3 sig figs with the 3, but I had 4, I mean with the 20. Actually, did I? I wrote 3. Did they give me 3 or did they give me 4? No, they did only give me 3, so I should stick to the 3. 3 times the 4 just gave me 3 sig figs. That means the 4, the 0, and the 0 are not sig figs. And that means that that number is in fact unitless. So now what I can do is I want to get the t by itself on one side, and I want to get all the non-t terms on the other side. So what I'm going to do is I'm going to subtract 1 from both sides, and I'm going to add 0.0785400 to both sides. And that's going to leave me with 1.141291 minus 1 plus the answer. Luckily, I still have it loaded up. Gives me 0.219831 on the left-hand side and 0.003927 T on the right-hand side. Uh, I should also mention that all four of the digits, the 3927, were significant, and in this case, only the uh, 219.07854 and the 54 or the 4 was not. So it's this one and this one are not significant. So I got 4 sig figs divided by 4 sig figs. That's pretty nice. So I can now see that T is going to be equal to 0.219831 divided by 0.003927, and that gives me 55.9794 degrees Celsius. Now that was 4 sig figs divided by 4 sig figs ultimately, so we do get 4 sig figs out of this again, if as if sig fig rules are really that valid. But that's the result. Any question with that one?
No, no question.
Yeah, that's a pretty straightforward calculation. It's kind of a pain in the butt, but it's at least it's a straightforward one. Have you ever used any thermistors or any devices like that, or had to replace anything in any kind of household units you might have?
No, no, I haven't worked with really any of this.
Gotcha. I've been fortunate enough to be a teacher, so you sometimes can't afford to buy what you want to buy. And multiple times of my heater's gone out, or my dryer's gone out, or my air conditioner's gone out, or my washer. But multiple times I've managed to find little temperature detectors, basically thermistors or other types of devices like that. And it turns out you can just pull them out, cut them loose, solder them back in, and 9 times out of 10 you can save yourself hundreds and hundreds of dollars. You just got to be careful because whenever you start messing around with electric devices like that, they inevitably, not only is it, a little safer to have the item unplugged, but it's not safe enough because of capacitors and stuff like that. You could still get the crap kicked out of you, but that is a nice sort of thing to understand. So when you start feeling things get really, really hot, there's almost always some kind of thermal device that's supposed to prevent that from happening. Uh, I've seen, for instance, dryers get so hot that the white paint starts to turn brown and burn. If you see that, that something was failed. Either the product was poorly designed and therefore didn't have a device to detect that temperature running away like that, or whatever the device was that was supposed to stop the temperature from running away like that is not working, and you might want to get it replaced. The cool thing is you can almost always just look in the diagrams and find exactly what part it is and what part number, but you can always just go to like a Ferguson and pick up stuff. I've been able to save heaters, dryers, washing machines, air conditioners, and televisions this way. But you do need to know a little bit of electricity, and you got to be willing to risk your own life because I sometimes get the crap kicked out of me with electricity. So I'm not saying do as I do. I'm just saying if you're smarter than me, do as I might would do if I was even smarter. All right, let's move on. The electric power is the next section in your textbook, and I've already went through that, but I didn't really give you any kind of derivation. So let me give you an idea of one way you can look at it. Remember from 241 that power is the instantaneous rate of change of potential energy, but sometimes they'll say it's the rate of change of work, but sometimes they'll say it's the rate of change of internal energy. All those are fair game. You can literally say any of that. Well, we happen to know that U is equal to Q times V in terms of electricity and magnetism. So we're going to use P equals du dt. So in so doing, we say P is equal to du dt. And remember, U is the electric potential energy, whereas V is the electric potential or just the voltage. So in this case, what we're going to do is we're going to say, okay, this is d by dt of Q times V. And that is, of course, dq over dt times v. If you assume, for instance, the voltage isn't changing in time, in that case, you get I, because dq dt is I, times v. So that's the way that it's typically derived. The expressions that I gave you earlier, which was P equals IV, and then plugging V equals IR into it, we got P equals I squared R, and then plugging I equals V over R into it, we get V squared over R. And these are all the results of power. Now, what is this power? What we're saying is if you have a wire that has a voltage across it, meaning if you took the voltmeter and stuck it at the red at one end, the black at the other, whatever that voltmeter read, if you took that and multiplied it by the current going through it, then that would be how much heat is radiating out of the wire every second. So, heat being in joules, and then heat per second being in joules per second, which is watts. That's what P equals IV is about. And that's usually the quantity that you have to look at if you're actually going to build something with a resistor. You need to look at the power capacity of the resistor to know whether or not it will stay ohmic in the range of voltages and currents that you're dealing with. So that's something to keep in mind. But that's the actual power equation. And I've seen this a lot. This might help you, especially if you're, you know, a lot of people, even though they're in the calculus-based physics, a lot of times they're not that quick with algebra and they get panicky. So I show this whenever I can. I've seen it in electronics shops. One of them is this, and that's just a way to use Ohm's law. If you want to, for instance, figure out V, then you cover up V and it looks like I is next to R. And if you write two variables next to each other, that means multiply. So obviously, if you want the voltage, you multiply I times R. If you want the current, you cover up the I, and then you see it looks like V is on top of R. So you take the voltage divided by R, and you'll get the current. That's the way a lot of people do this, especially especially on the technician side. But they'll also have written P I V for the same reason. So I just wanted to mention that. Now we really don't have enough time to go over the next example, so I'm going to go ahead and call it a day, and I'll just say the next example you should be looking at is 25.8 in your book. So we're going to cover something like that next, and we're going to finish off the rest of this chapter. Uh, it might be in our next meeting, but I think I want to do it by video and give it to you guys, and then maybe not meet for that particular one. I'll try to give you some times as to when I'm actually going to record them so that you can still come in if you want. But I think we got to do a little bit of time crunching there just to sort of speed up. So I might make some more videos tomorrow and Saturday. Okay. But you're free to go. Thanks for coming, Matt. Appreciate your being here.
Yep. Thanks a lot. See you next time.
You too. Have a good one.
Yep. You too.
Bye. Okay. So I guess that's it. Have a good one, everybody. Bye bye.